This story did not really begin when the world first heard about the object. In fact, it started days earlier when an unfamiliar visitor was quietly moving through the solar system without anyone realizing what they were looking at. Then, almost by coincidence, some of the most powerful observatories on Earth and in space ended up studying the same object. In 2025, an astronomical survey detected a faint object moving rapidly across the sky. At first, it looked like another distant comet. But as astronomers calculated its trajectory, something extraordinary became clear. This object had not originated around our Sun. Its path showed that it had entered our solar system from interstellar space, making it only the third confirmed interstellar object ever observed passing through our cosmic neighborhood. The object was designated 3I Atlas. Almost immediately, observatories around the world began searching their archives to determine whether it had been visible before the official discovery. And that search produced an incredible result. Earlier images from the Vera C. Rubin Observatory contained the object. The telescope had not been specifically searching for an interstellar visitor. It was still carrying out testing and validation observations, examining the performance of its instruments and data systems. Yet somewhere inside those images was a tiny moving point of light. The object had already been there. Nobody recognized it at the time because nobody knew they needed to look for it. Once astronomers knew its trajectory, however, they could go back through the archived observations and identify earlier appearances. Those images became extremely valuable because they extended the observational history of the object and helped researchers reconstruct its movement through the solar system. This is one of the hidden advantages of modern astronomy. A telescope does not necessarily have to know what it is looking for in advance. Sometimes the discovery comes later, when scientists return to old data with a completely new question. The Rubin Observatory is particularly well suited for this kind of discovery. Located on Cerro Pachón in Chile, the observatory was designed to repeatedly photograph enormous portions of the sky. Its massive telescope and extremely sensitive camera allow astronomers to detect objects that move or change brightness over time. That makes Rubin especially powerful for finding asteroids, comets, supernovae, and other transient phenomena. And an interstellar object is exactly the kind of target that can benefit from this approach. Once 3I Atlas was identified, scientists could compare images taken at different times and measure how its position changed against the background stars. The object also displayed characteristics associated with cometary activity. As it approached the Sun, material surrounding its solid nucleus became increasingly visible. Ice near the surface can transform directly into gas when heated by sunlight, carrying dust and other particles away from the nucleus and producing the diffuse cloud known as a coma. Depending on the direction of sunlight, viewing angle, rotation of the nucleus, and distribution of active regions, the surrounding material can form unusual structures. A comet does not always produce a perfectly symmetrical tail. Sometimes dust and gas can appear to extend in unexpected directions, creating shapes that look strange in photographs but can still be explained through ordinary cometary physics. That distinction is important. An unusual appearance does not automatically mean an unusual origin. The real scientific value of 3I Atlas comes from something much deeper than its appearance. It gives astronomers an opportunity to study material that formed around another star. Every comet in our own solar system is essentially a leftover piece of the environment that produced the Sun and planets. By studying its ice, dust, gases, and chemical composition, scientists can learn about the conditions that existed when our planetary system formed. An interstellar comet provides a completely different opportunity. Instead of examining material from our own cosmic neighborhood, astronomers can analyze material that originated somewhere else. That is like receiving a physical sample from another planetary system without ever traveling there. This is where the James Webb Space Telescope becomes especially important. Rubin and Webb have very different strengths. Rubin is designed to survey enormous areas of the sky and repeatedly monitor them. Webb is designed to perform extremely sensitive observations of selected targets, particularly at infrared wavelengths. When Webb observes a comet, it can analyze the light coming from the surrounding material and search for specific chemical signatures. Different molecules absorb and emit light at characteristic wavelengths. By studying those patterns, astronomers can determine which gases and compounds are present around the object. Water, carbon dioxide, carbon monoxide, and various carbon-bearing molecules can all appear in cometary environments. The proportions are especially interesting. Two comets can contain many of the same ingredients while having very different chemical ratios. Those differences can provide clues about the temperatures, radiation environments, and chemistry present when the objects originally formed. That is why scientists are so interested in the composition of an interstellar comet. The question is not simply, what is this object made of? The deeper question is, what kind of environment created it? And that question could eventually tell us whether planetary systems throughout the galaxy form in broadly similar ways or whether there are major chemical differences between them. One of the most fascinating possibilities is that an interstellar object can preserve information about a period of galactic history far older than our own solar system. Our Sun formed roughly 4.6 billion years ago. The Milky Way, however, is much older. Stars have been forming, evolving, and dying for billions of years, continually changing the chemical composition of the galaxy. When massive stars die, they release heavier elements into surrounding space. New generations of stars and planets then form from increasingly enriched material. An ancient interstellar object could therefore preserve chemical evidence from an earlier chapter of that process. It is effectively a natural time capsule. Instead of digging into ancient rocks on Earth, scientists can examine a piece of material that spent billions of years traveling between stars. That is why every confirmed interstellar visitor is scientifically valuable. The first confirmed example, Oumuamua, was discovered in 2017. It became famous because of its unusual shape, trajectory, and behavior, leading to intense scientific discussion and a huge amount of speculation online. The second confirmed interstellar visitor, 2I Borisov, was discovered in 2019. Unlike Oumuamua, Borisov displayed unmistakable cometary characteristics, making it easier for researchers to compare its behavior with familiar comets from our own solar system. 3I ATLAS provides another opportunity to study material from outside our planetary system. Each visitor is different. And because these objects pass through the solar system only once, astronomers have an extremely limited window in which to observe them. Their trajectories are open. They are not captured by the Sun's gravity. After passing through the inner solar system, they continue outward again, eventually disappearing into interstellar darkness. That makes early detection incredibly important. The sooner astronomers find one, the more time they have to organize observations. This is another reason the Rubin Observatory could become so important in the coming years. Its enormous survey is designed to repeatedly scan the sky, building a constantly updated record of moving and changing objects. An interstellar visitor could potentially appear in the data before scientists even realize what it is. Once its trajectory is recognized, other observatories can be alerted and begin detailed follow-up observations. That creates a powerful chain. One telescope finds the object. Another measures its motion. Another studies its brightness. A space telescope can examine its chemistry. And still more observatories can monitor how the object changes as it approaches and then moves away from the Sun. No single instrument has to do everything.